welcome. So, we are continuing our discussion on how to improve convergence rate of matrix solvers. That is, given a matrix solver for a large matrix, what are the techniques which can be applied over that particular given matrix solver, and the convergence rate can be improved, so that we get faster solution. So, earlier we have discussed about preconditioning techniques, and this session we will discuss on multigrid methods. So, we will focus again our discussion on what are the issues for convergence of iterative methods. So, let us think of a unit cube over which Laplace equation is solved using finite difference method. So, the geometry is already given and the governing equation is a second order finite linear differential equation, which is Laplace equation, and that is being used. We have all the known boundary condition. We have to solve this using computer methods. So, we will use something like a finite difference method and get a set of difference equations, which is essentially a matrix equation, and we have to solve that. We need to generate finite number of solution points on or control volumes to write discretized set of equations. So, this is a unit cube over which we take n points in each direction and get total n cube internal points, for which we have to write equations. Each point will have its own equation, and essentially we will get a matrix equation. Depending on the number of points, the matrix size will change. True, if I take, for example, if I take n 10, this is 10 by 10 by 10, total 1000 internal points are there. So, the coefficient matrix will be 1000 by 1000, and if I take n is equal to 100, this will be 10 to the power 6 by 10 to the power 6 matrix. So, the matrix size depends on the number of points, and we need to take large number of points in order to have better accuracy, because we have looked into at least finite difference methods where the accuracy is a function between the of the spacing between two adjacent grid points or nodes. So, if we increase number of points, this distance reduces and the code accuracy increases. The solution is more close to the physical solution. So, we often need to take a very large number of points, or which will yield a large matrix to solve these sets of equation. And now, let us look into the number of iteration steps required and how the error, that is difference L2 norm of difference between the solution vectors at different iteration level, reduces for a Jacobi point solver when in the same geometry we take different number of grid points. So, the first one is I have taken 4 internal points, and all the outer boundaries are Dirichlet boundaries, so I am not considering them. So, total 4 cube 64 into 64. Second one we have taken, so total 4 cube points. The second one is where we have taken total 7 cube points, and the third one we have taken, I guess, 12 square into 12. So, 12 cube points, 144 into 12. Yeah. So, how that means the first one is actually a coarse mesh which has very less number of points, and the errors will be large. Second one is little finer mesh which has more number of points. Third one is a finest mesh we have considered. Now, if we look into the number of iterations, the first one converged at 27 iterations where we have less number of points. Of course, it will be because the number of steps are also a function of the matrix size. So, there will be less number of steps. The second one converged in 127 iterations. The third one converged in 409 iterations. So, lot more iterations are required for the third one. Yeah. And if I see how the error is reducing, we will see that in the first one the error started from 10 to the power minus 2, and then after few steps it went to 10 to the power minus 3, 10 to the power minus 4, then came to 10 to the power minus 7, and then converged to the value. In the second one it stayed along at 10 to the power minus 7, the error is of the order of 10 to the power minus 7. Then it went to 10 to the power minus 8 and so on converged. The third one in 10 to the power minus 8 itself, it stayed for a long time, no number of iterations, then it required to converge the error from 10 to 0 in the first one. So, as we are increasing the matrix size, the number of iteration steps increase, it almost scales with the matrix size with the solution vector. And as we go to a larger matrix, the reduction is error is actually very slow. When we go to the finer value of the error may be reducing very fast from 10 to 6, but if we have to reduce the error from 10 to the power 1.2 to 10 into 10 to the power minus 8 to 1.1 to 10 to the power minus 8, that takes a lot of time. So, this is what we can look into the convergence pattern of the solvers, and we can essentially look into the convergence issues. The convergence for large matrices, when we have lot of grid points, the convergence takes large number of steps. When we have increased, this is convergence. When we have taken not convergence, I will correct it in the uploaded slide. When we have taken a large matrix, the number of steps for convergence is also very high. But we cannot avoid large matrices, because if we need a very accurate solution, we have to take a lot of internal points, which will give us a large matrix. The smaller order errors reduce slowly. That is, that when the error is of the order of 10 to the power minus 2, it is probably halved to from say 0.9 into 10 to the power minus 2 to 0.45 into 10 to the power minus 2 in say 10 steps. But if I think the error will get halved from 0.9 into 10 to the power minus 8 to 0.45 into 10 to the power minus 8, it will take probably 70 steps. That means, when the value of the error is small, the convergence is slow. So, there is something like a fluctuating function which is damped very slowly, because there is an asymptotic marching to the right solution. The rate of damping of this fluctuation function becomes slow when we go close to the actual solution. But that is again for the large matrices. For the small matrices, the error reduction even at 10 to the power minus 8 level is much faster than a large matrix. That is another thing to notice. Also, during each iteration, the number of operations are more in for large matrix. This is also very important thing, because we are dealing with an n by n matrix. Each iteration probably takes n number of operations in subtraction, addition, considering that few n or n square number of operations. When we are having a large matrix, n is very high, the number of our operations during one particular step is higher than when the matrix is small. So, a smaller matrix will require less number of steps to converge, as well as in each steps the number of computational operations is small. So, in total a smaller matrix will require very less number of steps if we consider the number of iterations as well as computational steps in each step in each iteration. However, I said we cannot avoid having large matrix. Things would have been very great for us if we would have been able to solve everything with a large matrix with a coarse grade, because the number of computational steps would have been less. But we really cannot operate at small matrices or coarse grids, because the accuracy will be compromised there. So, you have to operate with large matrix which is slow to converge, as well as in each step there are a lot of operations. So, we will see how both of these things can be tackled. Now, if I go back to, because we are discussing here with Jacobi iteration, if I go back to Jacobi iteration perspective, remember this discussion will continue based on Jacobi, which is the probably most basic iterative solver, but similar discussion is also valid for much developed iterative solvers like biconjugate gradient or GMRDS, but let us even with the preconditioned solvers too. But let us go to the very basic Jacobi solver, and at this lecture I will rather try to give you some key concepts on multigrid methods. As we discussed for preconditioners, the detailed of multigrid methods will take lot more lectures and lot more deliberations, many serious complicated mathematical analysis has to be done also, which we are not discussing here. We will just discuss about the concepts of multigrid methods. So, we focus our discussion only to Jacobi solvers, where these concepts can be at least reviewed with certain rigor. So, in a Jacobi iteration solver, the typical iteration step is given as k plus 1th value of x is equal to g x k plus f, where this is basically again comes from solving x is equal to b, but g is formed using some splitting of a. We have discussed it several times while discussing a few of these methods, starting from basic iterative solvers to preconditioners. Several times we have discussed this. So, G is called the iteration matrix. The system will converge for any initial guess x 0 if spectral radius of G or the modulus of the largest eigenvalue of G is less than equal to 1, rather less than 1. The convergence factor is given as rho is equal to rho G or the spectral radius of G, and lower the convergence factor, faster the convergence. Convergence rate is actually kind of having an inverse relation with convergence factor. So, if rho G is high, convergence factor is high, that means number of iterative steps will be high. If rho G is less or convergence factor is small, number of iterative steps will be less. So, we essentially for having a faster solution method, rho G should be small, but rho G again depends on the actual matrix A. So, given the matrix A, we cannot do anything with spectral radius of G except using preconditioning technique, where instead of Ax is equal to B, we are solving M inverse Ax is equal to B. But for general case, when Ax is equal to B itself has to be solved, we really cannot do anything with G. But if I have two matrices, one matrix solves faster than the other matrix, we can check the spectral radius of G for these two matrices, and the matrix which will have smaller spectral radius will converge faster, which will have smaller convergence factor will converge faster. So, we can look into different matrices created out of the same geometry and check their spectral radius of the iteration matrix, and we will see that which matrix will converge first or and why is it so. So, lower the convergence factor, faster is the convergence. Now, we consider a finite difference matrix. Matrix came out of using finite difference approximation on a partial differential equation with grid spacing h, and h is equal to 1 by n or 1 by n minus 1 by the way you define n. So, h is around 1 by n, n is the number of points along one particular direction. And then if I write down the 2D Laplacian finite difference matrix and split it for a Jacobi iteration, we will see that the spectral radius of the G matrix is of the order of 1 minus order of h square. So, if from Laplace equation, if I try to get a finite difference matrix, the iteration matrix in Jacobi or even for Gauss Seidel will have 1 minus order of h square spectral radius. So, in case I have a coarse grid where h is large, the spectral radius will be small. In case I have a large mesh where h is small, the spectral radius will be large, and precisely that is the reason that large matrices will take lot more steps to converge, because they have a large spectral radius. Because h is 1 by n, if n is high, this value is small. If n is small, number of points is small, this value is sorry, if n is high, this value is also high, because 1 minus 1 by n square, and if n is small, this value is small, so it converges first. So, this is the precise point, that if we have large number of mesh points, the iteration matrix will have a large spectral radius, therefore, the convergence factor will be high, convergence rate will be slow. If we have a small coefficient matrix and small number, which will come from considering small number of mesh points in the geometry, the spectral radius of the iteration matrix will be small, and therefore, convergence will be faster. So, rho G is of the order of 1 minus h square, h is equal to 1 by n, number of spacing in one direction, n is the number of spaces in one direction. In case with all Dirichlet condition, in our case with all Dirichlet condition we are considering, if there are n internal point, the matrix will be n cube by n cube. So, the number of the convergence will depend on the fact on this number n, what are the total number of internal points in one direction, if I assume that all points have same number of all directions have same number of points. Lower the value of rho, faster the convergence. That is what we discussed, that if we can reduce this value, we will get faster convergence. To reduce this value, this should be small, that means this number should be high. In order to have a high number here, this n should be this should be small. So, this should be rho g is small. So, 1 minus h square should be a small number. In order to have 1 minus h square small, h should be high. In order to have high h, n should be small. We can check it out. So, low number of points n and larger grid spacing will give faster convergence, and that is exactly what we have seen, that when you are taking less number of points, 4 points in each direction, the convergence is in some 27 points, and when taking 12 points in each direction, the convergence is obtained after 500 600 iterations. However, we are asserting this several times, as the accuracy improves with smaller h or larger n, large n systems are often to be used. So, the question becomes, I know that I have to use a large grid framework, which will give me a slower convergence, because h is being small, therefore, spectral radius of G matrix is small, it will give me a slower convergence. So, what should we do to improve convergence of this? One idea is using preconditioning technique. Is there something else which is incorporated in the method itself, how we are looking into the error and the convergence factor? Something can be done that, and one of the technique for doing this is a multigrid method, where instead of looking into small values of n only, we will club number of grid points and get another background mesh which has a large h, and do some of the iteration on the background mesh, reduce residuals, and then come back to the finer mesh, what we are going to discuss here. So, the question is that how we can improve the convergence even with the smaller h. So, we will again look into the convergence pattern for a large matrix. It is a matrix of 1353 by 1353, it is a different matrix, but it is again a large matrix, and we see that initial steps, it is from 1 to 0.22, 78% reduction in error is in one step. Then even when we are say around 10 to the power minus 2, 9.89 to 10 to the power minus 2, to half of it, which is maybe 4.25 to 10 to the power minus 2, it took 5 steps, right, and the error is reducing by 0.04. If we go later of the iterations, say 1.13 into 10 to the power, or 1.09 into 10 to the power minus 4 to 1 into 10 to the power minus 4. So, error is reducing at the rate of 10 to the power minus 6. That took 1.09 to 1, that took around 10 steps. So, the rate of reduction of error reduces as number of iteration increases. That means that if I look into the number of iteration versus the x minus xk plus 1 minus xk L2 norm. Finally, this should be 0, and this is initially high, and then it goes down very slowly it goes down, there is an asymptotic nature. So, it is a curve with varying rate, and at each iteration what is happening, the error is getting smoother. There are some small fluctuations in the value if we go to the previous time step, which is the difference from the converge solution, and this difference is coming to 0, and the solution is getting smoother in each iteration. However, this smoothing, so maybe I have this geometry, say x is equal to 0 to x is equal to L. this will be maybe my final solution, and I will see that the solution as I have given boundary condition is initially something like this, then it reduces something like this, then it further reduces something like this, and finally converges. So, how this fluctuation of the solution is damped to the final solution, that is important, and we are seeing these fluctuations reduce very slowly with time when there are small amplitude fluctuations, and the small amplitude fluctuations, because the error is small, are also long wavelength fluctuations. So, we will see what is the how are these fluctuation wavelengths. The error being a spatial function can be expressed as a Fourier expression. Any spatial function we can express as a Fourier expression in space, which is x minus x 0 is equal to e to the power a to the power m e to the power I k s. S is the spatial coordinate, it can be x y z if we think, but x is the solution variable. So, S1, S2, S3 are 3 different spatial coordinates. So, it is like a Fourier function. The errors with different frequency are minimized through the iteration. So, in a sense we can say that, say I have initially this should be my right solution. Initially I start with the boundary condition, I start with a solution like this. Later the solutions will be something like this. Later these solutions will be something like this, and so on. So, different there are solutions with different frequencies. There are some high frequency solutions, there are some low frequency solutions, which are getting minimized through these iterations. So, this k is for different wavelength, different frequency or wavelength. This k is for different wavelength, which is getting minimized through the iterations. If I have a coarse mesh, this is how the solution will look like, and I will get the converge solution in each point. If I have a fine mesh, then the solution is a much smoother one. So, what I am doing with each iteration, actually smoothing the solution, and this smoothness is done through the smoothness function has its own wavelength and frequency, which we are taking care, and it can be seen that the final solution, which if I have a large number of mesh points, I will get a very fine solution like this. This fits lot of long wavelength solutions, because it is trying to fit a very nice continuous and differentiable curve of very high order continuous and differentiable curve over number of points. So, the final smoothness, this smoothness comes through a large wavelength solution, and this large wavelength error, and these large wavelength errors are most difficult to minimize. Each frequency converges at different rate. Higher frequencies or low wavelength errors converge the fastest. The solution between two grid points, which is a very small wavelength, at one time step this can converge. Errors low frequency, errors with low frequency or large wavelength, which is trying to smooth the solution over the entire domain, converge in the slowest way. Convergence, and therefore convergence is held up by long wavelength low frequency components of the solution. The solution which is converging among many grid points has a wavelength of the order of number of grid points, that error is reducing in the slowest way. So, the large wavelength low frequency component error is the bottleneck thing in getting the solution, and that is what creating very slow convergence pattern at the 10 to the power minus 8 level, because it is trying to just smooth the solution in between a large number of grid points and trying to fit a very less amplitude, but large wavelength and also low frequency large wavelength smoothness over the error, or trying to correct a large wavelength low frequency error. Each iterative procedure has different rates of convergence for each range of frequencies. So, we will show something for Jacobi, you will see something you will see from Gauss-Seidel, something you will see from conjugate gradient, but essentially if we have large number of grid points, the final smoothing will take a lot of time, but each point will come to close to some of the ballpark value, but the solution will show lot of roughness and wavy nature because it has not been smoothened before we iterate and converge for the long wavelength solutions, and these long wavelength solutions take lot of time for all these solvers. So, essentially we need to find out some methodology to converge the long wavelength solvers, and this one methodology is called a multi-grid method. That is, the idea is to use different grid size to solve same problem. Why? Because what is high wavelength, say I have 3-4 points, and there is a smoothness function, like this, which has a high wavelength. So, this is h. If I compare with h, this is a very high wavelength and it will take a lot of time to smooth it. But if I use a different mesh size 1 and 2, this is, and now this is my h, the wavelength is actually of the order of h. This is the wavelength was 3h, here the wavelength is h. So, a high wavelength solution, which is a high wavelength solution for a finer mesh, is actually a lower wavelength solution for a coarser mesh, and that is the trick to handle large matrices using multigrid method. Because this is a geometric method, you already know the geometry over which you are solving the equations. Generate a large grid spacing background mesh over it, solve the equations on that, so that very fast you can solve the large wavelength solutions, and then go back to the finer mesh and correct the smaller wavelength solutions errors which are faster to converge, and that is the trick. Use a coarse background grids to reduce the long wavelength solution. First use a coarse background grid where the long wavelength small n and large h, which is long wavelength for a finer mesh, will be a short wavelength for coarse mesh. So, use a coarse background grid to solve the long wavelength errors, and then use finer grid to reduce shorter wavelength errors and to maintain the accuracy. So, basically this goes into using 2-3 different multiple layers of different grids to solve same problem. You have a same partial differential equation, you write a matrix equation with different grid size, and first solve it in coarser mesh and then come to finer mesh and get better accuracy, and then do some iteration between the mesh levels, so that the final solution is smoother as well as converges to the right result at the finest grid level, and that is why we call it a multi-grid method. So, we will look into the implementation of multi-grid method in the next session. Thank you.